Welcome, everybody, to this virtual event, the Space Connects Us event, hosted by Luxembourg's Asteroid Foundation and SnT. Thank you all for joining us today, and we are privileged to be able to talk to Astronaut Ed Lu, the Executive Director of the Asteroid Institute. Now, Ed has a Bachelor of Science degree in Electrical Engineering from Cornell University, a PhD in Applied Physics from Stanford University, and he flew on Space Shuttle missions STS-84 in 1997, STS-106 in 2000, and on the ISS Expedition 7 mission in 2003, where he spent 6 months on board the International Space Station. So he's logged over 206 days in space, and he performed an EVA, a spacewalk, totaling 6 hours and 14 minutes. Now that is surely enough for one very successful career. But beyond that, and what Ed is here to talk to us about today, is his position as Executive Director of the Asteroid Institute, which is a private non-profit foundation dedicated to planetary science and planetary defense against asteroids and other near-Earth objects. He's been instrumental in developing a software platform called Adam, which will allow us to sort of make or think of it as like a Google Maps of the solar system. So Ed, thank you so much for joining us here today. And just before you launch into your presentation, I just want to ask you about your time briefly in space, because 206 days in orbit around our planet, that must give you a pretty unique perspective on this world and what it entails.
Well, I don't know how unique it is. There are many people who have done similar things, but it certainly was fun. I'll say that much. It was quite an honor to get to go do that and get to see the Earth from that perspective. So really grateful for that.
And I believe as well that the backgrounds that we've been given today are actually made from photographs that you took while you were up there. It must be quite a sight looking back down at the Earth.
Yeah, absolutely. One of the things that you will always remember after having done something like this is just what the Earth looks like from that vantage point, and it's truly spectacular.
Well, Ed, once again, thanks so much for being here. I'm going to hand over the floor to you now. So I'll turn my camera off, and then I'll join you again once your presentation is finished. And for everyone that's watching, please don't forget, put any questions that occur to you in the chat box, and I'll ask them at the end. So Ed, over to you.
Thank you very much, Stuart. Let me get myself set up here. All righty. So I'd like to tell you all about the work that we're doing at the Asteroid Institute, which is a program of the B612 Foundation. So what we're really doing, as Stuart mentioned, is to try to build the first interactive mapping platform of the solar system. So, what do I mean by a map of the solar system? That means it's a platform that allows you to understand what is going on, to visualize, and most importantly, to calculate trajectories and location information. Why is that important? Because remember that everything in space is moving. So the most important part of any object in space is where is it and where is it going? So I want to take you on a little video tour of the solar system and give you an idea of what's out there. So this is a view from stepping way back in the solar system. These are the orbits of the various planets, and the green dots and so on, those are asteroids. What you'll see is that the solar system is dominated by asteroids. So this is the orbit of Jupiter here, Mars. Earth is right in here where my cursor is rolling around. The green dots are the asteroid belt. The blue and white dots are the asteroids in the inner part of the solar system, known as near-Earth asteroids. Now, these are all correctly displayed. These are the known asteroids in our solar system. Again, you see, there's 8 planets, and there's an awful lot of asteroids. So this is the orbit of the Earth right here. And as we zoom on in towards the Earth, these are the asteroids going by. And you can see how many of them are. In fact, we're moving even in closer. This is the moon going around the Earth. We'll go in even closer. Well, you'll actually be able to see the Earth as we get in closer. And you can see what's actually flying past the Earth at any given time, which is a lot. But here's the thing to remember. These asteroids that we're depicting here are just a tiny fraction of the asteroids out there. 99% of these asteroids are not currently tracked or mapped. So what we're showing here is 1% of the asteroids. Okay, the vast majority of our solar system is currently unmapped. That's the important thing. And if you don't know where those objects are, there's nothing you can do to visit them. There's nothing you can do to develop them. There's nothing you could do to avoid them if one of them is going to hit the Earth. If we're going to really do any of those things, develop space or protect the Earth from being hit by asteroids, you need to know where all these asteroids are and where they're going. And that's the big problem right now. So again, big picture view of the solar system. You can think of it as a swirling mass. If you think of it as a map, like classical maps of the Earth, you can think of these things as islands, all swirling around and moving. But it is a three-dimensional map, and it is in which everything is dynamically moving. So what do I mean by a space map? Well, so let me talk about a map that you're all familiar with, probably something that I had worked on in years past, and that's Google Maps. So Google Maps was revolutionary for one main reason, because it isn't simply a depiction of data. A modern map is made of two different things now. It's observational data sets. It's all the data that goes to build up the map. So in the case of Google Maps, that would be the images from space or from aircraft or from cars of things, and the terrain maps and all those things, the base data sets, okay? But just as important, it is all the services that make it useful. The services that allow you to put a pinpoint down and send a link to somebody else so they can see where that pin is. It's the services that say, what are the directions from where I am to where I want to go? What is the area of this? What is the distance from here to there? All those things are the things that when you add them to an observational data set, makes a map. So in the case of the space map, it would be these observational data sets. Those are the telescope observations of the solar system that we would use to give the data to know where everything would be. In the case of the services for what we're building, it is, given those images, what are the orbits? Where are those orbits going in the future? Which of those objects might hit the Earth? And what is the equivalent of being able to share a link that you do on Google Maps for that map? And that is what we're building. So the first of the services that we're building is actually an interesting one. I won't get into too many of the details here, but it actually allows someone to say, if I have a data set that I've taken, I've taken telescope images of the sky, and what asteroids are in here and what are their orbits? That turns out to be a very difficult problem, and one which we have found that the current methods in use actually miss a fair fraction of the objects that are actually there. And so we built a service called Thor, which means which is a method of analyzing a data set and spitting back observations. So we've used this to discover new asteroids. So the first data set that we picked out, we grabbed 10 new asteroids out of there that weren't seen. In other words, they're in the data set. Somebody's actually taken images of them, but they didn't realize they were there. So what's exciting about that is we can feed it ever larger data sets. And currently a really nice data set is one called the NOIR Lab Source Catalog, or NSC. It's 7 years of observations from a bunch of different telescopes. And when we took the first 2 weeks of data from this, out of the 7 years, and we found nearly 1,000. We found 900 and some odd asteroids that we discovered in it that were not noticed before. Here they are. And what does it mean to discover an asteroid? It means a point of light moving on a path which is consistent with an orbital track of an object around the sun. Okay, so random collections of dots doesn't make it an asteroid, but it has to follow an actual physical orbit. And so for an example, here's a number of points, locations on the sky, and the red line is a physical orbit around the sun as observed from the Earth. And in fact, you can see that there is an asteroid here because you can see it moving along these along the line at the proper time interval steps. And what that means is that our mapping platform can actually be used as a discovery platform, if you'd like, a virtual telescope for discovering asteroids in previously unseen data sets. So let me just sort of go back to the importance of mapping. You know, historically, maps are the driving thing for opening up of new frontiers. You know, from the 1500s, you know, that what I'm showing here is actually one of the earliest maps of the world depicting the continent. This is only in 1508 this map was drawn, and you can actually see how the things that are missing, but actually the things that are there too, is really quite fascinating. And maps were the subject of much investment and even competition among the European states in the 1500s, because they knew the power of maps. It tells you where things are. It tells you trade routes. It allows you to do scientific exploration, and also for prestige reasons, but mostly for economic and military reasons. They needed these maps. Into later years, the following map, the second one here, is a map made by the American explorers Lewis and Clark, who explored the North American continent, and with the goal of building these first maps. This is one of the maps that they built. You know, moving on to the current, as I mentioned, this is Google Maps, which obviously has had a large role in the development of commerce. For instance, many companies now are built off of Google Maps. These companies did not have to build their own maps in order to get started. So famous companies like Uber or Zillow or Lyft use Google Maps. And our claim is that the economic and scientific exploration of space, as well as planetary defense, the defending of Earth against asteroid impacts, will be driven by this space map when we fill it out. When we add 100 times more asteroids than are shown here, and we add all these services. So where are we right now? Well, we've got the space map is right now in beta test, internal beta test. And over the next few years, it will go to, so next year it will go to external beta. I'm showing here some of our hackathons. But the really interesting thing is going to happen in 2023. And that's because the largest survey telescope in the world will start operations for tracking near-Earth asteroids. And that is going to vastly increase the size of the data sets. So we're building the services in order to be ready for the data set, which is coming from the LSST telescope. This is the telescope now. It's being built by the United States National Science Foundation and Department of Energy. It is on a mountaintop in Chile. And it is an 8.4 meter diameter main mirror. And again, it will be the far and away the most powerful telescope for finding and tracking asteroids in our solar system. It will produce about 4 petabytes of images per night. So it's going to be amazing. This eye test of a chart, the summary of it is that the LSST telescope, when it turns on in 2 years, will discover asteroids at about more than 10 times the rate of all other telescopes combined. So we're about to be able to discover a lot of asteroids as long as we have our mapping platform up and ready to analyze that data and make use of that data when this turns on. So that's our goal over the next 2 years. So why is Adam important? So from a policy standpoint, from a pure planetary defense standpoint, we're going to discover a lot more asteroids once we turn on the space map. We'll be able to discover asteroids that would have been missed. So we've done simulations of the expected discoveries, and we've shown that you can do of the asteroids you miss by the current methods, we'll be able to cut that in half. Why is that important? Well, it turns out that approximately twice per week, the LSST telescope will discover an asteroid that has a chance of hitting the Earth. That's not to say that any or all of these will hit the Earth, but that that we will discover an asteroid in which we cannot rule it out just yet. And so this mapping platform, this ability to visualize and understand what these odds are, I think will be very important because it is open source. And that means that essentially we've shown our work, that anybody can go in and look at how these asteroid trajectories were calculated. They can run their own. And that's important because when you're talking about asteroids that might hit the Earth, it is extremely important that people understand and trust the source of that statement. I think we've all seen the types of things that can happen when you don't show your work. Over the last few years with the pandemic, there's been a lot of conspiracy theories. And part of that was self-inflicted because I believe a lot of the government agencies did not show their work. They made sweeping statements without being open about how and why they know what their statement was. So we can't do that. So the thing I'm letting you in on is that in 2 years' time, we're going to have a lot of potential asteroids that will be known that might hit the Earth. So that's an interesting place we're going to be in 2 years, and our space mapping platform needs to be ready for us to help people understand and share this data. So that's the summary of what we're doing, and I'd like to see if there are questions. So I don't know how we're going to work this. Stuart, will you just take the questions and then read them out,
yes.
Or how do you want to do this?
Yes, I'm also going to apologize for what on earth is happening with my green screen. Look at that. It looks like I'm beaming in like some kind of Star Trek thing that's happening there.
Perhaps you
Ed,
are.
Yes. But Ed, thank you so much. I mean, you've covered an awful lot of ground there in a very small space of time. Please, everyone who's watching, don't forget to send your questions in through the chat. But before I start asking our audience questions, Ed, I've got just a couple of my own. One of them is that I'm fascinated by the genesis of this project, and what was it that kind of really galvanized you to tackle this problem of planetary defense?
Well, when you mentioned the perspective of seeing the Earth from above, one of the things you can't help but notice is when you're out there is looking at the contrast between the moon and the Earth. The moon is covered in craters. Craters, in fact, on top of craters, to the point where the craters are even erasing other craters as they hit, right? And the realization that the Earth has been hit more than the moon, right? But you don't see as many craters because we have an atmosphere, we have weather that gets rid. We have plate tectonics and things that remove craters, so you can't see them. And when you think about it a bit, you go, well, wait a second. At some point, we're going to have to stop one of these things because the very large ones can actually wipe out life on this planet. We've come very close to losing it multiple times. The asteroid that killed off the dinosaurs is just one of many, many mass extinction events that this planet is suffering. And from your floating vantage point in a spaceship orbiting the Earth, you think, well, we could actually do something about this. And then, of course, you realize only if we know that an asteroid is coming, where some that asteroid is coming from. So in the end, it really becomes a matter of finding and tracking and building this space map to protect the Earth.
I'm fascinated by your history of the maps as well, because they're so important in us knowing where things are, how we navigate, what potential there is to be found. And yet here we are in this fundamentally different realm where the map changes constantly because everything is moving. I'm presuming that it's only the massive increase in computer power in modern times that is making anything like this possible.
Absolutely. Even building a static map like Google Maps requires an enormous amount of computational, and because the amount of data is staggering, and the computations required to do things like give you instantly the directions from where you are to your favorite coffee shop is staggering. When you get to the space map, the amount of data isn't as large yet. We don't have as many images of space as we do of the Earth, but the computations take much longer. They're much more involved. So in the end, you end up with a similar sort of need for a very large computational capability. And here's where cloud computing has made all the difference. Cloud computing allows you to have number of computer processors spin up automatically when somebody requests a piece of information. You don't have, and then when somebody else requests a piece of information, those things spool down and spool up at another location. And it allows you to handle requests like that. And so, building this map wasn't possible 10 years, 15 years ago. Well, 10 years ago it wasn't possible because we didn't have much of the data. That's getting better and better. And then when LSST turns on, it will really be much better. 20 years ago, this wasn't possible because we didn't have the computational resources to do it. And so
and you mentioned the data rate as well. Before I go over to the questions that are coming into the chat now, is there any way for you to paint us a picture for how much more data the LSST survey is going to give us a sense of the actual scale of the computational problem and the size of the data sets that you're going to be dealing with?
Well, the easiest way to look at this is really in terms of the numbers of asteroids discovered, I think. For near-Earth asteroids, which are just the ones that are out of the asteroid belt that could hit the Earth, currently all telescopes in the world combined discover about 2,000 new near-Earth asteroids per year. LSST will discover about 20,000 in just the first year. So, and similar numbers for asteroids in the main belt, the green ones in that image, or that moving map I showed earlier. So all the systems that we have today are built to handle the current levels of discovery that we have, not one that's 10 times greater. Add to that we want to improve the responsiveness of the calculations, the services, if you like, the ability to visualize and understand trajectories sort of on demand. Again, that's what makes the map useful. And those such services don't exist, at least for astronomy data sets. Okay, it's been pioneered in online mapping by Google Maps and by others, Bing Maps and whatnot, even Apple Maps, although I hate to say that. But they, so what is expected of a map today is very different than what was expected or needed of a map from a couple decades ago. And that takes computational power.
Well, we're going to go over to the questions now that are coming in from the audience. And Sumit Goski asks, is the mapping purely done by observing the light curves of these asteroids using telescopes, or is there any other critical data that's being used?
Yes, primarily it is done by, and it's not light curves. Light curves actually has a specific meaning, but it is the motion of asteroids across the sky as observed by telescopes. Now, a very tiny fraction like a couple of asteroids, also have radar data because they have come close enough to the Earth that a powerful radar can actually measure the distance. So in addition, some asteroids, and I mean a vanishingly small number of asteroids, have radar data also. And we use that to calculate their trajectories. Now, it's a bit of a math problem. You have to understand all the forces that act on an asteroid in the solar system. Those are primarily the gravitational influence of the sun, the other planets, corrections due to Einstein's theory of relativity, things like that, even down to the point where you do have to correct for very tiny forces such as the influence of the solar light by heating the different parts of the asteroid differently, which can actually cause a really tiny residual thrust from the emission of infrared radiation from the surfaces of the different temperatures across the surfaces of asteroids. Those things do have to be taken into account to accurately calculate where an asteroid is going.
It's absolutely fascinating. Now we've got some more questions here. Amelia E asks, how many asteroids near Earth do we know?
Well, currently we know about 20,000 asteroids that are in the inner part of the solar system. Okay, so those are the so-called near-Earth asteroids. That doesn't mean they're near Earth at every given point, but that their orbital trajectories are in the inner part of the solar system where Earth resides. About 20,000, but you can expect that number to double within the first year after LSST turns on, and then pretty soon thereafter, the majority of all asteroids known will have been discovered by LSST.
And Misbah Rashid asks, how much of a threat are asteroids to the astronauts aboard the ISS?
The threat to astronauts aboard the ISS is really not from asteroids. It's from orbital debris put up. It's human trash orbiting the Earth. By human trash, I mean pieces of metal, defunct satellites, even bolts and things like that, parts of rockets that have been left in space. So, when astronauts go up there and are worried about orbital, being hit by something, it's not an asteroid that they're worried about being hit by. It is a piece of human space junk that they are worried
about. Thinking about deflecting asteroids, Claudia Fiaschetti asks, are you confident that the technology exists to deflect incoming asteroids?
Yeah, I actually believe that the deflection of an asteroid, once you know that it is a danger to us, is far easier than the actual task of determining that a particular asteroid at a particular location is the one I need to be worried about. But we haven't done it for real. That's about to change. About 3 weeks ago, NASA launched a mission called DART, which is called the Double Asteroid Redirect Test. What it is actually going to test the deflection by a tiny amount of a real asteroid. So that spacecraft is on its way towards an asteroid, which is actually a double asteroid. And it is going to just simply run into that asteroid. It will impact in about, it's roughly 9 months from now, maybe 10 months from now. I don't know the exact how many days it is till impact, but it's simply going to run into that asteroid at high speed. And just like a car accident on the freeway, that does affect the speed of that asteroid. It's more like a bug hitting the windshield of a car, though. It's a tiny change in the velocity. It's, in fact, if you measured it as a percent, it's about 1/1,000,000th of 1% change in velocity. But the amazing thing is that is sufficient to change the timing in which an asteroid is going to encounter the Earth, such that you can prevent an impact. 1/1,000,000th of 1% is the level at which our precision is in both measuring asteroid velocities and predicting whether or not something is going to hit the Earth. That makes a difference. So by running into this, fairly large, 160-meter asteroid with a small spacecraft at high speed, you actually change its velocity by a very, very tiny amount. And so again, that's extremely basic physics. It's not extremely basic engineering because flying something into space and hitting an asteroid that's a tiny little object in the sky, at approaching it at these enormous speeds is a difficult engineering challenge. But the physics tells us this is going to work. So there's no question that this is going to work. But we do need to show that the engineering works.
And there are other ways to deflect asteroids as well, including ways that you have pioneered and worked on as well.
Yeah, there are multiple methods, and there is no answer to the question, what is the best way to deflect an asteroid? Because it always depends upon the particular case that you're talking about. It's like asking, what's the best movie? Well, it depends, right? Or what's the best soccer team? Well, it depends, right? It depends upon the way you're asking, what your goal is here. Now, this simply running into it called a kinetic impactor, that is one method. There are many other methods, some that are controllable. Note that running into it is not very controllable. Where the new orbit that it is in afterwards, a little bit hard to predict. That's one of the goals of this mission, is to help understand how much impulse you actually give to an asteroid, because you blow a lot of material off the surface. You create a crater on the asteroid. And so it's inherently uncertain how much it's a crude weapon, if you'd like, a crude tool to change the trajectory of an asteroid. There's controllable methods like gravity tractors, something that we invented, which is far less powerful but far more controllable. And you simply hover a small spacecraft nearby. You don't run into it. You hover near it in such a way that you actually gravitationally tow it with a tiny force of gravity between your spacecraft and the asteroid. Now, I'm hoping we do a test of that, because likely in the future, when you do have to do this for real, let's say we find an asteroid that's going to hit the Earth, you will almost certainly, in fact, I would say with 100% certainty, we're going to use a combination of methods. Something like a kinetic impactor combined with something like a gravity tractor, such that you can do a sort of a large scale movement, by large scale meaning of 1/1,000,000 of 1% movement of the asteroid, followed by a much more controlled one to put the asteroid in a final trajectory, which is exactly where I want it. So I miss the Earth by a certain amount, and it doesn't come back and hit me again later.
Now, we go back to the questions from the audience, because Sumit has a great question here. And he says, does Adam also track interstellar objects like Oumuamua, which might pass through our solar system? And how much of a danger do these objects pose for our planet?
So first off, for those who don't know it, Oumuamua was the name given to essentially an asteroid which came through the solar system a couple of years ago. But what was interesting about it is it didn't come from the solar system. And we know that because it's not orbiting the sun. Its velocity was too fast to be orbiting the sun. It actually came from some other star system, we don't know which one, and was on its way through the solar system, moving at very, very high speed. So there are other objects known like this. Not a lot, just a handful. This was a fairly famous one. And yes, our mapping system, our discovery system, can be used to track objects like this. Also comets. So we actually did discover a comet in a data set, which was, we can't claim the discovery because somebody else also discovered the comet in using other data sets. So it was not noticed in the data set that we used, but somebody else using a different data set had previously claimed that discovery. So we have a moral victory of discovering a comet. And comets are not that dissimilar to objects like Oumuamua, because they do come into the solar. These are objects which are gravitationally bound to the sun, but just barely. Those are comets. Now, Oumuamua is even coming from a little bit faster. Therefore, it was not bound to the sun, or is not bound to the sun by gravity. And but these are not the objects that are threatening to the Earth because there are so few of them. Remember, go back to that image of all the swirling massive asteroids running around the sun. There's millions of those asteroids, only a handful of objects that are like Oumuamua.
And in a follow-up question to that, Sumit asked, how do you validate your findings and the accuracy of the trajectories that you predict?
That's a great question. And that's one of the things that we are, remember when I said it's open source and transparent? What you have to do is you have to take your calculations of trajectories of objects done in the past, then propagate them to the future, meaning, let's say I take all my observations of a particular object up to 10 years ago, let's just say, and I'll ignore the observations done after that. Using that data, I can predict where that asteroid should have been 9 years ago. And then you look to see where it really was. And you ask the question, how accurate was your prediction then? How accurate was your prediction 10 years ago of where it was 6 years ago? I project forward 4 more years to a point in time 6 years in the past, but still, and see how accurate it was. Now you do this for thousands and thousands and thousands of asteroids. And you have to demonstrate that your predictions were later borne out to be true. Okay, and not only your predictions, but that your uncertainties, the range of values that you say, well, in a year from now, 2 years from now, 3 years from now, this asteroid will be at the following location with the following uncertainty, that had better match the actual uncertainties that you discover when you look at thousands of cases. And that has never really been demonstrated by any system. It's claimed that it is, and I believe that they have, but nobody's ever shown their work. And I think that's going to be crucial.
Indeed. Well, we have Ed for just a few more minutes. So if you've got any questions, now is absolutely the right time to put them in the chat. We're going to go through the ones that we still have to get through, Ed. So we're sort of moving into a bit of a rapid fire round for you now. And we've got a question here from Raya. This is a nice light one here. What was it like? What made you apply to become an astronaut? And what should she do if she wants to become an astronaut?
Well, my path was rather unusual in the sense that I wasn't planning or building towards becoming an astronaut. It's not a career goal of mine. At the time, I was a scientist, but I was also a pilot. And a friend told me that you can apply to become an astronaut. And I thought, oh, that sounds like fun. So that's what I did. I sent in an application and it was accepted. So it wasn't something I built toward. Now, I think I was relatively rare among the astronauts in that sense. Most of them had actually been trying to build their careers towards this. So my story is a little bit different. As for you, I think it depends very much upon, at the moment, from where you are from. And the reason for that is that almost all the astronauts today are hired by their respective countries as national astronauts. So for instance, if you're an American citizen, you can become a NASA astronaut, or from one of the European Space Agency countries, you can become an ESA astronaut, or Japanese Space Agency, or Canadian Space Agency, etc. Now, that is changing because private flights are beginning to be flown. Obviously, at the moment, the costs of those are extremely high, but those will come down. In the same way that in the 1920s, very, very few people had flown in an airplane, whereas today you don't even think about it. People do it all the time. In fact, at any given time, there's hundreds of thousands of people aloft in the air at any given moment. In fact, there are right now. So, this is going to change. How quickly will it change? I don't know, but I suspect that the costs of flying in space are going to drop considerably. Now, two things there. One, which is that is the cost if you pay for it yourself. But that also means that there are going to be jobs of people flying things, as a service for those who are paying. So, many of the people flying at this very second are pilots, they're flight attendants. There are people flying at this moment. They're doing things that would have been incredible to someone from 100 years ago. Getting up in the morning and going to bed that night on a different continent. And it's commonplace today. And I suspect that is going to happen too as we open up space.
Well, back to the Adam software, and Solo wonders, when can students use the Adam platform?
We're going to begin to open things up out of internal beta in the next several months. But it'll be to a small group of mostly scientists because we'll be using them as beta testers and so on. So I expect it'll be a good part of a year before we have students really using the mapping platform.
And I think time for just one more question, and that comes from Sumit again, and he's got an acronym that I don't know how to pronounce, but let's give this a go. It says, according to NASA's CNEOS, CNEOS data, it's predicted that Bennu has a high probability of hitting Earth in the 2060s, since it will be flying closer than the moon. Is anything being done currently to address this particular threat?
Yeah, Bennu is a near-Earth asteroid. And by high probability, I think it's an impact probability of something like it's in the range of 100,000, I believe, something like that, 1 in 100,000. So it's not high in the sense of like, betting odds being high, but it will certainly be coming close. Now, should future observations show that in fact it is on a trajectory to hit the Earth or coming very close that we need to do something, then we do have things at our disposal, like kinetic impactors, like gravity trackers, and so on. I don't believe right now anyone that the risk is high enough yet to do anything, but obviously there are, we'll keep monitoring that one. Remember though that the risk is from the asteroids that we haven't yet seen. Okay, there are many asteroids like Bennu out there that will be coming between the Earth and the Moon. Thousands between now and that time. Which one, if any, do we need to be worried about is the question. LSST is going to help us answer that. And the space map.
Well, Ed, thank you so much for your time today. It has been truly fascinating to hear everything that you've been telling us. It almost feels like we're sort of seeing behind the scenes of things that we're going to hear an awful lot about in a few years. It's like we're on the verge of a whole new way in which we are going to be finding, studying, tracking asteroids and working towards defending the planet. So thank you so much for sharing your time and your explanations with us today. And thank you to all of you for watching. And thank you, of course, to SnT and to the Asteroid Foundation for hosting this Space Connects Us event. And we hope to see you again soon. Goodbye.
Thanks, everyone.